multiplicity arises across the uses of Morgan theory, especially if you look at this picture, you have multiplicity by taking limits. Another way to understand is that two pieces of hypersurfaces touch each other. They have to be identical to each other. It's called the strong maximum principle. So what I eventually found is that if you propose to some other functional of H, this strong maximum principle is broken, so you have some hope to continue. Okay, so that's strategy. So we try to approximate the area functional by Lagrange. I use a Lagrange multiplier. So the functional is written as follows. So suppose, as I mentioned earlier, that the type of surfaces we are interested in can always be written as a boundary of some site. So I pick one of the open sets bounded by sigma, and I take a smooth function. So this is a smooth function. So then we consider this Lagrange multiplier functional. So this Lagrange multiplier for the area, so as you use A as related to the function H as defined over the open site. So this is area of the boundary, subtract the integral of H. So this is a functional that I use with Jonathan in our study of the quantum mean curvature surface and surfaces with prescribed mean curvature. Okay, so if we do the first version formula for this new functional, we would have the following. So say that if a smooth hypersurface is a critical point of this functional, so what we would have is that if you take the first version for the area part, you get the mean curvature. So actually this is a mean curvature with respect to the outer normal. So this is the mean curvature for that sign. Is equal to the ambient function H restricted to sigma. So this is usually called the prescribing mean curvature. Type equations of PMC. You can call it PMC surfaces or PMC equations. So in our study of the existence theory with Jonathan, so we realized that this type of equations can break the strong maximum principle in the following way. Okay, so so we called it like so the one-sided maximum principle. So this PMC equation satisfies so this one-sided maximum principle as follows. So it can be shown by drawing the following two pictures. So say if you have a piece of surface such that its mean curvature vector is given by h times nu. So if you have another piece that points the same direction. Okay, so let me just assume a special case. So let's assume that H is strictly positive. And we found that we can find a generic set of H so that this one-sided maximum principle holds, and positive functions is a subset of this generic set. So if H is positive, you have two pieces whose mean curvature points to each other, say like two spheres or two cylinders point towards each other. So we were able to prove that the touching set is small. So they can only touch at a set of codimension 1. So example, spheres touch over a point, or cylinder touch over a line. Okay? So that's one case. So the other case is that if they all point to the other side, so they can never touch. So fortunately, in our study of the CMC and PMC problems, this will be the only two cases that appears. So for instance, if the two pieces have their mean curvature all points upwards, they can still be identical to each other. That is the other side. So this is a good side. You have another bad side, and the bad side never appear. Okay, so if you are in the right position, so this strong maximum principle tells you that the limit is either like properly embedded with multiplicity 1, or has a touching set of codimension 1. This is a strong accidental embedding, which is also sort of multiplicity 1. Okay, so here we have 1 point to take a break. But we'll go back to see how we can use this functional to approach this multiplicity 1 problem. Very much for the introduction, and always very nice to be back at the Institute. So what I want to talk about today are, in fact, two results, and I want to talk about both of them because they're related, both in terms of technique. There's a certain technical tools used in each of them, and also thematically. So both of them have different things to say about basically the variational structure of the Yang-Mills functional. So I should say at the outset, although I'll repeat this is joint with Casey Kelleher, who's here, and Jeff Streets. So I'm
not a gauge theorist, so I view these more or less as some ideas in spectral geometry applied to gauge theory. But let me set up the picture here. So in a minute I'll specialize to 4 dimensions, but at least at the outset I have a closed Riemannian manifold. And I have a vector bundle E over X. So vector bundle. And then I assume that I have a connection, so given a connection, and I'm going to assume it's a metric compatible connection, so I have a metric as well in the vector bundle. Nabla, so this is going to map, sections of E across smooth vector fields to sections of E. And then I'm going to let F be the curvature of this connection. Then I can define the Yang-Mills functional. So, which is just the L2 norm of the curvature for a given connection. So 1 of a connection is the L2 norm of curvature. Okay, so what are critical points? We want to take a variation. So if we take a family of, so I have a connection, and the first variation, I'm going to vary it by one form that takes values in the bundle. So any variation can be written this way, so it'll be one form taking values in E. And then what I can do is take a first variation of the functional. Oops. And using the definition of the curvature and first variation, what you get is, I guess there's a factor of 2 here, and you get the inner product of curvature of Nabla with the exterior derivative that's induced by the connection acting on this one form, D. So if I have a critical point for the Yang-Mills functional, this is 0 for all such B, so if I just integrate by parts, I get the Yang-Mills equation, which says that the adjoint applied to the curvature is 0. So that's the Yang-Mills equation. And now, by virtue of being the curvature connection, we also have the second Bianchi identity, which I can write this way. So this is second Bianchi. Now, if E is just a trivial bundle, the manifold cross real line, then in other words, F, you think about F just being real value 2 form, you get real value 2 form. So if F is a real value 2 form in that case, a trivial bundle, then this would just be the equation telling you you have a harmonic real value 2 form. Okay, so as I mentioned at the beginning, I want to eventually specialize 4 dimensions, so let's go ahead and do it now. So from now on, always and forever, the dimension is 4. So there's several special features of 4 dimensions that I'm going to take advantage of. So let me go over those. Some are obvious, some less so. The first one is conformal invariance of the functional. So if I conformally change the metric, you can just track through how things scale in the functional, and in 4 dimensions it's scale invariant. So in particular, if G tilde is, say, E2W times G, then the energy, oops, the Yang-Mills energy, excuse me, doesn't change. Write it this way. Well, I'm mixing metrics here, but anyway. Okay, so now let's. So another feature of 4 dimensions is that we need to exploit is self-duality. So the bundle of 2 forms in 4 dimensions we'll split. So let's assume not only that X is 4-dimensional, smooth, closed, but also let's assume it's oriented. So I can split the bundle of 2 forms into self-dual and anti-self-dual 2 forms. So let's say self-dual and anti-self-dual. So correspondingly, the curvature of a connection will split in this case. The self-dual and anti-self-dual part. So so we've got the first variation calculation of the Yang-Mills functional, the Yang-Mills equation here. But it turns out that if one of these pieces vanishes, that automatically satisfies the Yang-Mills equation. So the basic idea is that, well, let me record this now. So just using Hodge theory, you can, so the adjoint operator shows up in the first variation. All right, and then depending upon your conventions, your sign conventions and everything, there might be a plus or minus here, but anyway, you can rewrite this. The adjoint in terms of the actually exterior derivative, and then conjugate by the star operator. This leads to the following definition. So a connection is self-dual or anti-self-dual if the curvature is self-dual or anti-self-dual. So i.e., if, let's see if I get this right. So self-dual if the minus part vanishes, and anti-self-dual if the plus part vanishes. And then you can check using this formula that if, so maybe put it over here, you just write it a little bit smaller maybe. So if Nabla is self-dual or anti-self-dual, then Nabla is a Yang-Mills connection, satisfies the Yang-Mills equation. All right, so you just check this by using the second Bianchi plus this expression for the adjoint. All right, so it's a critical point, but actually you can say more. But to do that, you need to consider some topological invariance, so namely introduce the Chern classes. So the second Chern class bundle is given by, and again, it depends on your conventions, but for me, I guess it's going to be minus 1 over 8 pi squared. And the form you integrate after you simplify turns out just to be the difference squared of the self-dual and anti-self-dual part of the curvature. So this tells us very quickly that, in fact, not only are self-dual or anti-self-dual connections critical points, but actually they have to be global minimizers. Right. So you can rewrite the Yang-Mills energy in terms of the second Chern class in the following way. So the Yang-Mills connection is plus or minus 8 pi squared second Chern class, and then plus 2, and they have the self-dual or anti-self-dual part of the curvature just by splitting the curvature and then using the formula for C2. Well, if you want to think about it as an SU2 bundle, that's fine. I don't care. So the point is we get a lower bound of this form. And I want to highlight this and hopefully not erase it because I'm going to come back to this later on. So the corollary is that, so nabla is self-dual. So if nabla is self-dual or anti-self-dual, then nabla is a global minimizer of the Yang-Mills functional. Oh, yeah, so I should say, whether it's self-dual or anti-self-dual, in either case, the term used collectively is instantons. So instanton solutions are of fundamental importance in the applications of gauge theory to four-dimensional topology. But that's a very different story from what I want to talk about today. So let me begin to explain what I have in mind. So as I mentioned at the beginning, this is really a talk about some variational properties of the Yang-Mills functional. So the first kind of results I want to talk about are so-called gap results. So let me phrase it this way. So same setup. A vector bundle over a four manifold. And now let's suppose I have a Yang-Mills connection. So here's the kind of question I want to ask. All right, so one kind of, if it's a Yang-Mills connection, it could be an instanton. So maybe it's, let's say self-dual. Well, actually, the way I'm going to write it is anti-self-dual. So it could be anti-self-dual, so the plus part of the curvature vanishes. So that's one possibility. But suppose that's not the case, so this is not identically zero. Then is there necessarily some discrete gap in the Yang-Mills energy? So a little more precisely, does there exist a number delta, which is certainly going to depend on the bundle, such that once the self-dual part of the curvature is small enough, then actually we have to have an instanton, so it has to be self-dual. So either this, for a Yang-Mills connection, either it's self-dual, excuse me, anti-self-dual right here, or it has to be above this energy level. Okay, so there's a number of results along this line in the literature. Let me hit on a few here. Actually, the first one I want to hit on is not exactly in this kind of vein, but it's nevertheless important. So let's do it Bourguignon and Lawson back in 81. Okay. And so this is, I guess, this is of the sphere. So the result is following. So here I'm doing things in terms of the L2 size of the self-dual part, but they did it in terms of the L infinity size. But anyway, it's the same kind of spirit. So it turns out they have a number, which is 3, and they say if the L infinity norm is less than 3, again, for a Yang-Mills connection, right? Then you have the ASD. 3. Yeah, 3. So it's later on I'll write down a Bachner formula, and when I write that Bachner formula down, and you specialize in the case of the sphere, it's a competition of two terms, and you just realize if this hypothesis holds, the positive term beats the negative term, so it goes down to. Okay, but in the direction of L2 results.
In these cases, history sharp.
No, I guess it's sort of, I'd have to think about what you mean by sharp, because in a small set, are you letting it to be a little bit bigger than 3, or? I know where the 3 comes from, and there are examples where, okay, so there's a standard solution on the core sphere, the BPSP instanton, where you will have identically equal to 3. All right, so in that sense, I guess you say it's sharp. But anyway, I want to concentrate on the L2 statement. Okay.
It doesn't depend on E. It could be any vector below E.
Here, yeah, well, yeah, I think because the algebra doesn't matter for this one, yeah. Because it's from a Bachner formula. So.
Well, in all honesty, Bachner-Weissenbach usually has a curvature term from the bundle and one from the manifold over which it sits.
Right, so this is S4, and that's what's feeding into the 3.
Right, but there may be a curvature term from the bundle which means...
That's what this is.
Oh, that's where it only shows up there.
Yeah.
What's in the Bachner?
Yeah, exactly. Yeah. Okay, so, but in the L2 direction, there's 2 results about the same time. So, Minnow, I guess this is 82, and Parker. I'm going to group these together, different papers, but I'm going to group them together because they're very similar in spirit. So the answer is yes, there is such a delta. And, okay, what does delta depend on? It's not explicit. And what does it depend on? So I'm going to be a little bit vague here because when eventually I'm going to write down this Bachner formula anyway, it'll be easier to be more precise about what everything depends on. But so the volume of the manifold, and then there's some condition on the curvature of the metric of the manifold, which it's a kind of positivity condition. I'll come back to this later. And then some kind of dependence upon a Sobolev constant. And then, of course, the vector bundle. And the basic idea here is, so for this result, as I said, it's a pointwise Bachner argument. For this result, you use the Bachner argument, and basically you want to do kind of an epsilon regularity, and that's why there's a Sobolev constant dependence here. Right? So it's really epsilon regularity in disguise. So it just says if you have L2 smallness and you beat the Sobolev constant, the only solution is 0, is what it boils down to. And then more recently is the Feehan. So this will be 2016. So here, so again, the dependence is kind of complicated, but so Feehan, he drops this positivity condition, and he replaces it with a kind of genericity condition of the metric. So he defines what he means by a good metric, and he shows this as a generic property, and then, so there is such a constant, but it depends upon the metric sort of in a non-obvious way, and then the bundle. But nevertheless, dropping this positivity condition that I'll eventually talk about is actually kind of crucial because this actually has topological implications. So this is a more general result. But in all these cases, I guess you don't really, you can probably estimate delta, but you don't really have a concrete number. Okay, so let me state the first result. I want to discuss. I'll call it here A, and this is says that yes, there's a delta, and we can quantify it, and it's more or less sharp, or at least sharp in certain cases. So same setup. But we also make a curvature assumption that I'll get to in a second. So closed, oriented. So nabla is the Yang-Mills connection. Okay, so then the result is I'll state it now to explain the notation. So then nabla is an instanton. Well, let me put the self-dual part. So then the connection is anti-self-dual, or you get the following inequality. So it says the following. Our result only holds if the scalar curvature of the basis manifold is positive. And we measure that in a conformally invariant way by looking at the Amavi invariant. So this is the Amavi invariant. And this is less than or equal to, so I got to get the constants correct here. So 3 gamma 1 of E, I'll explain in a second. The L2 norm of the self-dual part of the curvature, plus 2 root 6, the L2 norm of the self-dual part of the Weyl tensor. Now, what is this gamma 1? So it's a constant that you can compute, and it depends upon the bundle. But there is a universal upper bound. So where gamma 1 depends upon the bundle, but the universal upper bound is always less than or equal to 4 root 3 over 3 by your conventions. So in particular, for example, if you're on the sphere, right, then this is explicit number, right? This is just the volume of the sphere. Well, what is the volume? The square root of the volume of the sphere times the scalar curvature of the sphere. So anyway, this is explicit for a sphere. You can get number bound on this constant, and then of course the sphere is conformally flat, so the Weyl tensor vanishes, so this term's not there, and so you get a lower bound. So generally you get a lower bound whenever this term is bigger than this term. But if you apply it to the sphere, let me just mention that, and I bet I erased it. I didn't. Hooray. Okay. So the corollary is that if you're looking at a bundle over this fourth sphere, and then let me, so that we can pin down a value of gamma 1, let's say an SU2 bundle. Just because we know the explicit constant here. And again, nabla is the Yang-Mills connection. Then either it's anti-self-dual, or this estimate written out tells you that the Yang-Mills energy is greater than or equal to 8 pi squared times the absolute value of the second term class plus 16 pi squared. So compare that with this general inequality here. So this is the same as this, right? So it says that, all right, if you're not an instanton, if you're not an anti-self-dual, then the gap here is 16 pi squared. And that 16 pi squared is there are examples where you hit that value. This is full. This is full, yeah. That's why you bring in the second term class, yeah. All right. So there's two. This is a wow. So there's 2 ingredients in the proof, and I'll postpone both of them to the second hour. Well, the second part of the talk, I promise they won't both be 1 hour. So the key ingredients. So the first one is, I guess I should have said this when I first wrote down the formula. So one, a little bit unsatisfying things about previous results, just in addition to the fact that you couldn't really quantify these constants, is that it doesn't really reflect the conformal invariance of the Yang-Mills energy. So all these things, all the data here is kind of sensitive to conformally changing the metric, but the Yang-Mills energy is insensitive to conformal change in the metric. So and this estimate here is conformally invariant. Every term is. Okay. So and that's crucial for us, and we exploit that in the proof in a key way. So what we want to do is not, if you give us a base metric, we don't want to necessarily use that to do our estimates. And in particular, when we write down the Bachner formula, we do not want to write down the Bachner formula with respect to the given metric. We want to first conformally change it to a more optimal metric. So it's a choice of conformal representative. That's really the only new idea. And then the second key thing is this Bachner formula that I keep referring to, which is well known. So it's just applying this idea to the Bachner formula. And I'll write down the Bachner formula, and there's the second part. Okay, so that's the first thing I want to talk about. All right. And then the second thing I want to talk about are index estimates. Okay, so this first result says you're either at the minimum energy or you have some fixed gap above that. So if I have a non-minimizing solution, so I'm above that energy cutoff, then the next question is, okay, what can I say about the variational structure for those solutions? Are they not minimizers? So you want to look at the second variation and look at the index. You could have directions where the Yang-Mills direction, the second order, where the Yang-Mills energy could decrease and increase. So that's the theme of the second. Okay, so the setup now is we always have a S4 Yang-Mills connection. And now we want to do a variation to second order. So take the same kind of variation we talked about before, but take the second one. Oops. Okay, what do you get? Well, I guess the way I'm going to normalize this is a factor of 2 here. You get an index form. So what happens is some operator, I'll call it J for Jacobi, that acts upon B, and you take the inner product with B. Right, so what is this operator? So this operator is the following. It's in terms of the rough Laplacian. I should say, by the way, my Laplacian on Euclidean space is this, okay, just to make it clear on the signs and everything. So it's minus the Ruffle-Laplacian, and then there's another second order term. So basically what's going on here is this is just going to be the Hodge-Laplacian. So it's another second order term, and then a term involving the curvature of the bundle. So I'll write it this way, and I'll say something in just a minute about this. And then a term involving the curvature of the base. Okay, so I'm using a lot of abbreviations here. So the bracket operation can be extended to a bracket operation on fundamental value 1 forms, and then 2 forms. It can be extended to a bracket operation on 2 forms with a 1 form. So this bracket here will map 2 forms across 1 form to 1 form. Let me not write it out because there'll be a boatload of indices and it won't tell you anything that you need to know for this.